So welcome to our today's session. We'll start with Fabrizio Rompineve, who will tell us about new physics for cosmological concordance.
Thanks, and thanks also for inviting me for this, for giving me the opportunity to talk about this topic. So yeah, I will deviate a lot from the topics that we have been discussing in the last days. So this is more of a cosmology topic with data, with handling of cosmological data, in particular CMB data. And yeah, so it's work that I've been doing. It's a topic that of cosmological concordance that I've been working on in the last years, both with people in Europe, in Spain, and in the US at Tufts University, where I was before now moving to CERN. Okay, so first I want to tell you a bit of the motivation, what got me interested in this story of cosmological tensions, cosmological concordance. So how I got to this topic, and then I will describe what they are, and hopefully at the end I'll manage to present some of my own contribution to this thing. So it will be of topics, since I don't know what the how familiar you are with the topic. Okay, so I just want to introduce a bit. Okay, so that's I'll skip very fast here. That's just a standard chronology, how we think that the history of the universe went. So there are high energies. These are the ones that we've been discussing in these days. So there are, I think, belong to beyond the standard model physics. These are highlighted in red. Others may occur at these energy scales as well, of course. The epoch that I will be particularly concerned with today instead is that of recombination. So these are low energies for all purposes that we're discussing in these days. And also large scale structures, so even lower energies in the universe. So the attitude that I had when I started getting interested in this topic is that of the physics of dark sectors. So since today there is no evidence at the moment for new physics interacting with the standard model, then it's a realistic possibility, as you all know, that those fields interact with the standard model only gravitationally. This is the kind of dark sector idea. And that means that there are no signals probably in astrophysics or colliders lab. Nonetheless, there are lots of cosmological signatures, since cosmology is about gravitational interactions. So there are indeed, this paradigm be tested a lot by cosmological observations. This paradigm of dark sector, as we've heard also last week in Sava's colloquium and in general in several talks, can be also motivated from a point of view of extra-dimensional theories, where you have a lot of extra fields coming out of compactification. So in particular, you can have a multitude of dark gauge groups, so similar to QCD, light pseudoscalar fields like axions, and also heavy scalars moduli that can change constants and so on. So I encourage you to look back at Sava's talk for all these interesting things. And so the interest then, my interest is then in how to detect these dark sectors, how they can affect the cosmology. There are several epochs at which they can affect the cosmological history. So here, as a function of redshift is increasing on the right. You can see first there are structures, matter properties and interactions can affect large and small scale structures. For example, as you know, axions, glue balls, and so on, specific properties lead to changes on small scale structures. Then there is the CMB, where extra species affect the expansion rate and also the perturbations. So also by looking at the CMB, of course, we can learn about the existence of dark sectors if they're there. And then, of course, there are gravitational waves that can be generated by phase transition, topological defects, and so on and so forth. Some examples of dark sectors that will lead to these signatures. And I, in these years, try to contribute to these three ways of detecting dark sectors. So I won't go into details of this work, because today I'm talking about something else. But I encourage, if you're interested, to ask questions about the other things. So in this talk, as I said, I will focus on the epoch of recombination and so on this the observable that can constrain dark sectors which are very light, so they're relevant at the temperature of electron volts or below electron volts, and also on large scale structure, they are also able to constrain, of course, dark sectors which are would to different structure formation than cold dark matter paradigm. Okay, so now I can be a bit more specific about what I mean by concordance model. So currently we are using, we believe that the universe is very well described by lambda CDM. That's the concordance model. It's a model that relies on 6 parameters, of which the important ones for the sake of this talk are the first 2. These are the baryon and cold dark matter abundances. Then there is the expansion rate today, H0, and then there are the amplitude and the index of primordial density fluctuation. So these are kind of the parameters. Actually, the first 2 and the last one will be more important for us today. And how do we infer the values of these parameters? How do we measure them? Well, those values are most precisely inferred by fitting the cosmological model, the lambda model, to the CMB temperature and polarization power. Most recently done, of course, by Planck. And then there are other early universe probes, such as large-scale structure and so on, which agree with CMB using lambda CDM models, give a consistent picture of results for these cosmological parameters. Here I just mentioned some of them. However, it's important to keep in mind, for the sake of this talk, that if you change cosmological model, since it's a fit to data, if you change the model, also the inferred values of parameters can change. Yeah, that's crucial for addressing concordance with late universe probes instead. So late universe probes are ways of measuring parameters more directly with less model dependence. So you don't necessarily assume a cosmological model, or at least not to the same extent as you do for the CMB. And one of such measurements is that of H0, so the expansion rate of the universe today, which is, for example, done using the distance level method, for example, with standard candles such as Cephids and supernovae. That's what the Schuss collaboration does, using Cephids as the first ladder of the first rung of the ladder. And then there is also the tip of the red giant branch calibration for the ladder. So the different ways to calibrate the ladder and infer the value of H0 using the distance redshift relation. There are other ways to measure the value of H0. There are, for example, time delay in gravitational lensing. This is what this holy cow experiment does. And then there is a promising way to have a very precise measurements of H0 in the future using gravitational waves and standard sirens. Okay, these are some ways to infer the value of H0. And there are other late universe observations that one can do to further test lambda CDM. That is, for example, measuring the amplitude of density perturbation at late times using so-called weak sensing surveys and galaxy cluster surveys. So some of those, for example, DES and the KIDS and the HSC and so on. So the idea here is that you have some, so you have some background galaxies, and then you have the foreground, so the clustered lens galaxies. And by observing how the light from these galaxies is deviated by the presence of the foreground, infer the distribution and properties of a large-scale structure. And in particular, these surveys aim at measuring a parameter that is a combination of the amplitude of density perturbation at late times, the sigma, which essentially you can think of it just as the amplitude of the power spectrum, very much like we have AS from the CMB. This is at a later time, sigma. And then it's combined with omega matter. That's the total abundance of matter, of non-relativistic matter in the universe. So they aim at measuring this parameter, which can also be inferred from CMB, and then you can compare and see whether they agree or disagree. So the current situation, specifically on these two parameters, is interesting. Disagreement between early and late universe measurements of the Hubble constant. So in particular, here I'm highlighting the one from Schuss from the supernova Cephids calibrated distance ladder, which give a significantly larger value of H0 than the one inferred by fitting lambda CDM by Planck. And you can see also the other late time measurements that I was mentioning. There are some that are more in agreement with Planck, but then they are There is an analysis also by the RIS group for this tip of the red giant branch stars, which actually gives a significantly different value of H0 again. So it's not clear what the situation between these two distance ladder measurements is. But you can see that more or less the late time measurements seem to agree better with the distance ladder method than with early time measurements. So the 4.4 sigma between these two values. And for S8, there is a similar, although much milder tension. These are weak lensing surveys combined in this analysis from 2020. This is the joint analysis. So you can see again, there is a tension at the level of 3.26. This analysis, other analysis more recent from kids, for example, report 2.8. This year free, if you look at the cosmic share results is 2.3 sigma. And there are very recent new results from yesterday or 2 days ago, different analysis of cosmic share that confirm a 2.5 to 2.8 sigma tension.
Fabrizio, I have a question.
Yeah.
Sigma 8 is just one of the things they can measure, right? Structure at 8 megaparsec. But it's not all the information. You could do 4 megaparsec, 16 megaparsec. So
okay.
Do they throw out information, or do they do global fits, or just do they only use this S8?
Yeah, I don't know exactly whether they also check on other scales. Probably, I guess so. I mean, I guess probably they also find the same. I mean, I guess the choice of 8 megaparsec over H today is just a convention, but I think I would say, yeah.
But there's information on this scale.
Right, all the scales that they can probe, of course, I guess they give information on all the scales that they can probe, right? So I think fixing to 8 megaparsec over H today, I guess it's a, yeah. They should have information also on other scales, I guess, yeah. Yeah.
So this S8 is not among the 6 parameters that you showed before, right, for lambda CDM. So
exactly. So maybe let me.
Okay.
So sorry. Let me ask. Finish the question, please.
No. So I just wanted to see how the.
Right. So it's not among the parameters I was talking about at the beginning, but you can see here there is AS. That's the amplitude of the power spectrum of the primordial power spectrum, right? Then by assuming a given model, you can evolve this power spectrum to late times by assuming a given cosmological model, and then that will give you the sigma 8 essentially. So here, I mean, when I talk about tension, I always talk about tension in lambda CDM models. They always assume lambda CDM model, flat universe, GR, okay. Yes. Okay, so when you look at this discordance, then you can have two attitudes. One is kind of optimistic, positive, at least from the point of view of looking for new physics. That is that this disagreement can be an indication of the presence of some light-dark sector, which is modifying the lambda CDM picture. For example, some interaction in dark matter or some extra component that does not behave just as dark energy or dark matter, but transition between the two, something like that. Of course, you can always have the skeptical attitude. You should have it. Should always keep it in mind that this can also be due to systematics, still to be discovered, or statistics. In the case of the S8 tension, we've seen that the tension is not so strong as for H0, so it could also be statistics. Okay, so this is always worth keeping in mind. But for the sake of this talk, of course, the first attitude. And then I want to first review briefly how to keep tension in these measurements. So I focus now on H0. Okay, so I will explain how Planck measures in a very simplified picture. You can look at this paper for more details. And then what kind of new physics, what kind of particle physics we need to effectively increase the value of H0 that is inferred from CMB. So the angular size of the comoving signed horizon at CMB last scattering is very precisely measured by Planck by just looking at the peak spacing. So this quantity is very constrained, measured to a great precision, and in a given cosmological model is also given by a ratio of the comoving sound horizon and the comoving angular diameter distance. These quantities are defined as follows. So one is just an integral of this sound speed divided by the Hubble rate at redshift z. from Z star, so the redshift of the surface of last scattering, to infinity. So in practice, this quantity is very sensitive to physics that occurs slightly before recombination, okay, slightly before Z star. That's the sensitivity of this quantity. On the other hand, the angular diameter distance instead is the integral of 1 over h from 0 to Z star, so it's the opposite. It's sensitive to the physics of the late universe, and in particular, you can see it's sensitive to the value of h naught today. So essentially, by having these two quantities, by having theta star measured through the CMB, and these two quantities, you see that if you want to have a larger value of h naught, then you need a smaller value of dA. But in order to keep this fixed, since it's measured to great precision, then you also need to reduce the sound horizon. So that's the strategy. And this is basically in pictures what I was just saying. So what you can do if you want to keep this fixed, you just, you reduce everything. You reduce both dA and RS. And in particular, one way to reduce RS, this integral, is just to increase the value of h close to recombination, just before recombination. So you need to inject some energy. You need to have some extra energy just before recombination. Okay, so there are practical challenges in doing so. First, you want to keep all the CMB angular scales possible, not only the one that I was showing before, the sound horizon, but also the not only the last scattering surface, but also quality and photon damping, because these are very constrained by the CMB heat. Then you also want to make sure that you're not only fixing, you're not taking care of CMB, but you also have to make sure that you're not spoiling agreement with large-scale structure data or BAO, since now we have a lot of data also from these later epochs. Then your model, if you have a model that addresses the H naught tension, it should give a larger value of H naught without including any prior from the local measurement. It's not just that you get a larger value just because you input the prior from shoes. And you should also be mindful about the S8 tension. So if this model increases the other tension, then you're not really restoring concordance. Finally, when you include the H naught measurement in the fit, then you should have a significant improvement over lambda CDM. Otherwise, if you're adding 10 parameters, of course, you'll be able to match the picture, but you're not improving the fit, really, the quality of the fit. Okay, so then there are theoretical challenges. What I mean here is more particle challenges. First is whether there is a particle physics model, not just an effective cosmological fluid model, but also a particle physics model that gives these features. And then you would want to explain why there is energy injection somehow close to matter radiation equality. So that's sort of coincidence. So in that sense, this fits with the topic of this week, cosmic coincidences, in the sense that you need something that coincides with radiation equality, more or less. Okay, so let's look at some possible suspects for these particle physics suspects for this a solution to this problem. And the first one is the simplest one is dark radiation. So, of course, if you want to add extra energy, you can do it in the form of radiation. And that's, of course, the best way to do it. You just increase rho by the amount you need to increase H, similarly H. And that's what we call that connect, right? So the extra number of relativistic species in the early universe normalized to neutrinos. Okay, I don't need to go into the details of this because you all know what I'm talking about here. So this adds only one extra parameters effectively. Then, of course, if in a specific model, it may be more than one parameter. However, this does not work. Not enough to fix this problem, as we checked, and also has been noticed even before by Planck, that even when you include the shoes prior, so here I'm reporting results, even including the shoes prior, you don't have a sufficiently large value of H naught, and also the improvement over lambda CDM is not particularly significant. In fact, if you don't include the shoes prior, you know that there is a very strong bound already from CMB on the amount of dark radiation that you can have. And then with this value here in this plot, and you see that the value of H naught is very low compared to shoes. So this does not really work in reducing the tension.
Can you remind me what's the shoes prior?
The shoes prior is 74.3.
Okay.
Plus or minus 1.4 meters over second. Yes. So in practice, if you don't include the prior, you have a tension with the delta NF model at a level of 3.5 sigma, probably 3.7, 3.8. I don't remember exactly now. Okay, so you're not doing a great job of solving this this tension. The second, I thought, simplest scenario, which I won't have much more time to talk about, is that you can also, instead of, in the Friedman equation, instead of changing rho and h, you can also change m Planck. So cook up a model where G Newton changes in the early universe, so it's smaller in the early universe. So this kind of modified gravity scenario. However, and there is a field theory realization with a scalar field non minimally coupled to gravity, which has the interesting feature that it naturally features a transitional matter radiation equality. This is because the field is sensitive to the Ricci scalar and gets a mass from the Ricci scalar, and this mass is negligible compared to Hubble during radiation domination, but not negligible during matter domination. So that's maybe can play a role in explaining it. However, quantitatively, when you look at the quantitative results for H0, is very similar to dark radiation. So in that sense, it doesn't work by itself. So I will go now to the next aspect, which is the one that's currently significantly debated. It is the presence of some light scalar field that would behave as dark energy matter radiation equality, and then would dilute faster than radiation. So it's these are so-called early dark energy scenarios. Okay, here I'm just drawing a potential which is flat enough such that the equation of state, when the Hubble drops to the then you have a transition from a dark energy behavior to some kind of exotic fluid which scales faster than radiation. Okay, there is also an alternative scenario referred to as new early dark energy. You have a phase transition. Of course, you can also have a dark energy behavior by simply having a scalar field stuck in a local minimum and then you transition. Now here you have to find a way to justify. I mean, you need to understand whether it's possible to have an equation of state larger than 1/3 and equation of state parameter larger than 1/3 in the after the phase transition. Okay, so these are roughly speaking the early dark energy scenarios. The troubles with these scenarios are, first of all, that when you include all data, including large scale structure, BAO, and so on, you find that the tension remains quite large, 3.6 sigma, 3.2 sigma, depending on the specific model. However, interesting, shown recently that the conclusion is altered if instead of Planck IL data, you use ACT data combined with Planck LOL, then it seems that with this data set actually seems to prefer the presence of early dark energy. So there is an interesting, maybe interesting situation here between CMB data. Yes.
So if you remove the IL data from Planck, already the discrepancy is much smaller, right?
Yeah. So yeah, IL is the one that, yeah.
By how much?
So you mean using what? LOL and WMAP, for example? I don't remember now.
Yeah,
exactly.
something like that.
Yeah, I don't remember exactly. But this paper uses the latest ACT data release and finds evidence for a early dark energy component. When you use ACT with Planck combined with Planck LOL. So maybe there is something interesting occurring with the IL that would hint at something like that. Of course,
yeah,
it has to be.
So if you go along these lines, then the solution would not be new early dark energy. It would be just within lambda CDM. No?
Well,
so if there is a, okay.
Yeah, that would mean that. Yeah, I see your point.
So we'll not be here talking if it was. I think the discrepancy is less than 3 sigma, if I remember. If you remove the high L of Planck.
Within lambda CDM.
Yeah.
Yeah, it could be that this is, yeah.
Yeah.
So anyway, this conclusion is within early dark energy, so not within lambda CDM. That's what I'm saying, is that if you add early dark energy, yeah. Okay, so the other problem is that, of course, you would want to have some well-motivated physics behind this W larger than 1/3 behavior. So the fact that the fluid scales faster than radiation. The ED potential that is usually assumed is tuned. It's a cosine cube, so it's a tuned potential. It's not clear where it should come from. In new early dark energy, it's not clear where you would get an equation of state larger than 1/3 after the transition, even though there are some ideas related to the anisotropies of the bubbles. And I'm happy also to discuss some other ideas that I've been thinking about recently. The other problem is that to angular scales fixed in the CMB, you will have that you will find that you need to increase other abundances of, for example, dark matter and shift other cosmological parameters. And this in particular leads to strong constraints on new early dark energy, in that the fit to large-scale structure data is affected in these scenarios. As you can see here, this data set here, FS, stays basically for large-scale structure analyzed with the effective field theory of a large-scale structure. So you can see that when you include this data set, the posterior on H0 remains far away from the shoes region, just to say exactly that, precisely that this data set constrain early dark energy. And also the other thing is that you see they lead, since they lead to a shift in the dark matter abundance, you need more dark matter to accommodate for models. Unavoidably at late times, you have the spectrum, the power spectrum is actually, the amplitude of the power spectrum is even larger than in lambda CDM. So you're exacerbating the S8 tension in these models. So this is kind of the traveling situation with these models. And what we added to the story recently is this idea to, in a sense, take care of this aspect. So what if
there was a in the archive to this analysis by Kamionkowski, right?
Sorry, can you say again?
Yeah, that this criticism was so answered by Kamionkowski.
Yes.
Group saying that indeed that, I mean, that didn't kill the idea. I remember, but I don't know why.
Yeah, so there the debate is that, so the debate is exactly how you assess these tensions and how you, so there are some points in the space, let's say, of these parameters that appear to be better than what I'm showing here with this posterior. So it's just that this posterior you see is highly non-Gaussian. So there seems to be some problem when you do a Monte Carlo analysis of these models, okay? But it's not, yeah, I would say this is not, I mean, it's unavoidable that physically you obtain this, this issue here in the power spectrum when you add more dark matter. Okay, so there is a simple way of, we thought of a simple way to avoid at least part of this problem. That is to add, so what we need is an additional abundance of dark matter in these models, unavoidably as a shift due to the presence of early dark energy. So what if this dark matter comes in the form of scalar dark matter? It doesn't need to be cold dark matter. Usually it's assumed that it's a cold dark matter component. But as we know, ultralight scalars are particularly interesting and motivated in a sense. I'm talking about ultralight axion dark matter. And they have this peculiarity that they suppress matter fluctuations compared to cold dark matter above a certain wave number. So if the wave number of your mode is above the Jeans wave number at equality, where the Jeans wave number is basically this, in the case of scalar dark matter, then all these wave numbers the growth of all these wave numbers is suppressed as compared to a universe with cold dark matter. So you see that the mass scale that seems to be interesting here, this is the range of K-modes studied by large scale structure surveys. So the mass range that seems to be interesting is very, very low. It's 10 to the minus 26 electron volts. Now, if you want to understand this better, this is due to the scale-dependent sound speed of the scalar field perturbations. We can go back to this if you have questions later. So one can look at the following effective dark sector model, where you have a decaying dark energy component, which is similar to early dark energy or new early dark energy, something essentially that goes from dark energy to a fluid that scales faster than radiation. But also add an ultralight axion with a standard axion potential, so just a standard cos potential and generic conditions of one in the field range of the axion. And this dark sector model then if you fix the mass of the scalar by using this 10 to the minus 26 electron volts that I was hinting at before, then introduces parameters to lambda CDM. It's the fraction of the energy density in the early component. and the redshift at which the transition from dark energy to a fluid that scales faster than radiation occurs. And then you have the matter is mass. It has to be only a small fraction, but as we will see, this is enough. Even a small fraction is enough to address the problem. Okay, so here I'm now going to results, and then I will conclude. So the results, when you fit the mass to be 10 to the minus 26 electron volts, are as following. If you first look only at a data set which includes all early time measurements, so Planck, BAO, and also the BOSS data analyzed with the effective field theory of large-scale structure, then you can compare the results of this dark sector model with lambda CDM, and choose 2 sigma is here. So you see that the tension which choose in this model now is less than 3 sigma without the late universe measurements and with the effective field theory of large-scale structure. So this you want to compare with 4 in new early dark energy. And when you include the prior now, so the late universe observations also of S8, then you obtain that the decaying dark energy component is detected at 4 sigma, meaning that 0 is excluded at 4 sigma in this fit. Okay, so you see how 15% of energy density, 12% of energy density in this component combination brings you very close to shoes. .8 sigma tension without with priors. Again, this is to be compared with the stronger tensions in lambda CDM and in early dark energy, as I was telling you. And again, when you include the prior, you find the 2 sigma evidence for an ultralight axion component, which represents more or less 5% of the dark matter today. So very small fractions of the dark matter today. Now, in terms of axion parameters, this corresponds to a decay constant on 10 to the 17 GeV, and again, a mass of 10 to the minus 26 electron volts. Okay, so yeah, here you can see also how the matter power spectrum is suppressed. The dashed is the dark sector and the black is in lambda CDM. You can see that it's suppressed compared to lambda CDM. So it's precisely the effect that we wanted to achieve. And the so this kind of demand for H naught and SA, the 2 curves are the dark sector model. When you shifts very nicely to the region hinted by shoes and SA and cosmic shirt surveys. And even when you don't include priors, you see that you have much better consistency than in lambda CDM.
Fabrizio?
Yes.
Okay, so can I ask? So can you remind what is the model here? It's both.
Yes, so it's a model that includes that adds to lambda CDM. It adds, sorry, let's see. It adds a decaying dark energy component. I call it decaying dark energy because early dark energy to me is a bit confusing. This decaying at recombinate.
Mm-hmm.
And then it adds on top of that, it also adds a light axion dark matter component. Okay. Now I will discuss later about a way to unify both.
Can they be unified?
I have some ideas, so I will present them in the last slide, really.
Fabrizio, here.
Okay, another question? Oh, sorry, go ahead.
Oh, go ahead, it's fine.
So by prior, you mean the shoes prior?
So in this analysis, we are adding late universe observations step by step. So we are first not including them.
Yeah.
By prior, I often refer to shoes prior. The shoes prior 74.03, blah, blah. When I say S8, instead is a prior from cosmic share measurements. They measure S8, so that's another prior. So, yeah.
Do you vary the mass of the neutrinos in this analysis? Because it's also 5% of the dark matter. So
yes, we keep in this analysis fixed as like in Planck.
Yeah, but I think you have to. I mean, in particular for the S8, it may have an impact because precisely it's 5% of the dark matter. Right?
Actually, can you fit it with a combination of, instead of adding an axion, can you change the neutrino mass and fit the thing?
Well, I guess you cannot, otherwise it could be resolved, but
So yeah, to that question, I don't think I haven't seen that that you can fix it really by just varying the neutrino masses. And to the early dark energy. Yeah, I don't think you. I mean, I haven't seen this investigated. Now the thing is that the early dark energy makes SA tension worse. So if you want to address it in lambda CDM, you can try already with lambda CDM with varying neutrino masses. I don't think it solves the tension. If you add early dark energy, you're sure to make it worse because.
This is the confusing part. I'm sorry, but it's the confusing part exactly because you're asking. It changes the way neutrinos do the shape. It's same. They have a gene scale, right?
Yes.
Free streaming scale. So by changing the neutrino mass, you change the gene scale for 5% of the dark matter. I don't know if it's going to work. It's just, precisely what Diego is asking. So that's why.
Yeah.
Say that again? No, but only for neutrinos. Did they do it for both with dark energy and this? Because I think this is the question you were asking too, right?
Yeah, I see. I understand the point. Yeah, you're saying since you need more dark matter, why don't you try first with varying neutrino masses? So that would be interesting. Yeah, definitely. Yeah. Yeah. Okay. Yeah. No, definitely an interesting point. Right. So that was I was showing here. So the quality of the fit you can assess. There are several ways, and everyone has its own taste. But let's say if you look at the full data set, including all priors, and so this is a full. There is everything here: early universe data combined with late universe data. Then you obtain that the tension, the residual tensions with the priors here is below 1.5 sigma, both for H0 and for S8. And the delta chi-squared is -18 with 3 extra parameters. So now it depends on what criterion you use to assess the evidence of this model CDM. If you use this revised Jeffrey scale, this is strong evidence over lambda CDM. But again, I am not a statistician in this thing, so I would refrain from making that this is very strong evidence over lambda CDM. Okay. Just saying that it's not negligible. You see, for example, dark radiation was leading to the delta chi-squared of -2, something like that. This is -18 with two more parameters. Okay, so finally, since this is a particle physics conference workshop, I want to mention an idea to unify these two components. Now, if you look at this idea starts by looking at the axion mass and decay constant that you get from this fit. Okay, you get 10 to the -26 and 10 to the 7 electron volts and 10 to the 17 GeV for F. And if you think that this axion is getting the mass from some low energy instantons, very much like in QTD, then you would infer a lambda, so a confining scale associated to instanton effects of order electron volt. Okay, so what this is saying is it may suggest the existence of a confining gauge sector with a confinement scale around the electron volts. And the question is whether this can be a decaying dark energy component, because then you would have, a sort of QCD where you have a dark gauge group and an associated axion, very much like QCD with a QCD axion. That would be kind of, I think, a unified, in a sense, scenario to address both tensions. Now, in previous work with people in Barcelona, had investigated some the behavior of confinement phase transition. Certain confinement phase transition can exhibit the phenomenon of supercooling. So in particular, you go from the deconfined phase to the confined phase, but you go through an epoch of supercooling. And in that case, essentially, you get stuck. You can think of it as getting stuck in a local minimum of the free energy. In that case, basically, you have exactly a dark energy behavior. So in these theories, a dark energy behavior for a while is possible. The open question here is rather whether you can have a equation of state parameter after the phase transition that is larger than 1/3. So this will remain basically as an open question.
Sorry, but is
Yeah.
that all? I mean, you need to explain that how you create the sector.
Yes.
And it's a thermal sector, so, and it has a lot of energy density. So at the same time, and a lot of degrees of freedom. So why isn't it ineffective during BBN? Why isn't it affecting BBN?
No, so basically, so what you need is that it's 15%, right? It's 15% at recombination. But if there is an epoch of dark energy, then you see that it's very easy that it grows very fast. The energy density compared to the background grows very fast for a short epoch. So, so basically what you have is that originally this dark sector behaved like a hot gas of gluons, of dark gluons, radiation, right? And it's a very, very negligible part of the energy density of the universe. Then at some point, as it approaches the confinement phase transition, it starts behaving like dark energy. So its energy is approximately constant, and therefore the ratio with the energy density of the background grows very rapidly. Okay, so in the paper we checked that basically basically at the redshift. So there is a nice story here that yeah, if you check, you basically can have that this dark energy behavior starts at Z of 10 to the 4 or something close to 10 to the 4. That's already enough from there to matter radiation equality to have a big increase in the sufficient increase that you need, and you avoid delta NF from BBN, for example. This always remains a very subdominant component of BBN. Okay, so okay, that was kind of yes. It would have to be. Sorry. Yeah, the temperature of the dark sector is lower than the temperature of the thermal plasma. Yeah. It starts. So if you want, yes, it ends the local minimum of the dark energy behavior starts significantly before recombination. Sorry? Significantly before recombination, around Z10 to the 4 or something. So, yeah. Okay, so let me conclude since I'm already late. So I just wanted to motivate first the interest in this kind of tensions comes from, in my case at least, comes from the physics of dark, so from the possibility that new physics interact gravitationally with the visible universe. And cosmology in particular, large-scale structure data, paradigm, especially when these dark sectors are light. It's very challenging, however, to reconcile observation, late universe and early universe observation. So most models try to address one tension and then they increase the other one, or they just have some dark radiation, which, as I showed, doesn't before. And then I described this dark sector model of components that seem to can address better both tensions. And this test is brought by a set of future observation, including stage 4, that will be able to probe ultralight axion dark matter at the % level. That's the level that is required to rule out possibility. There are other observations, as we were discussing with Diego, also coming from the formation of soliton dark matter that may be interesting. The realization of this idea, however, as I tried to show, challenging in the sense that we don't know exactly how feasible it is to have an equation of state larger than 1/3. And there are also other mechanisms here beyond this idea of early dark energy, new early dark energy. In particular, there are recent ideas related to mirror world dark sectors that I haven't been able to discuss now, but I'm happy to talk about them later. Thanks. Sorry for taking too long.
So the other question I have for you is, how would you know? Let's say that this is how the world works. You explain this anomaly to some precision. How would you know that this is the model of the world?
So there are so in order to know that this is the model, first of all, you would have to detect essentially a 5% component of ultralight axion dark matter. This can be done of mass 10 to the minus 26 electron-volt. This will be eventually done at least by CMB stage 4. The claim is they can get 2% level at this mass. So if there is a detection there, you already have something, a hint that this has to do with the S8 story, at least. For the decay in dark energy component, then future CMB studies will be able to probe even more the presence of this transition from dark energy to something that scales faster, right? So again, you could be, but now the question is, how would you know that it's exactly a phase transition? Yeah, then it starts getting a bit more intricate. You could think about gravitational waves, but of course, gravitational waves here are the frequencies extremely low. This is extremely low because it's happening at CMB, right?
Then you have B modes.
Hmm? You would have B modes. This was we were discussing. Yes. Yeah, the amplitude is particularly small, but
what about non-Gaussianities from these?
Right. So this is what we were discussing, what you pointed out in one of our discussion. That's definitely interesting. So I haven't thought exactly about it's exactly the phase transition. Yeah. Yeah, this is what I was trying to. You mean?
The action gets its mass from so that they are both related, and it's not just a random.
Yeah, yeah. So that was that's the idea that I was trying to I was mentioning, right? So the gauge sector and the instantons of this gauge sector give the mass. Then, so the mathematics, at least at the level of the.
No, I'm asking experimentally, not at the level of theory. I know you can make it work in the theory part. How would you know that you discovered this extra?
How would you know that the action is getting its mass from this thing?
Related from this thing, yeah. How would you know that the action is getting its mass from this thing?
Yeah, I mean that's. Yeah, I guess. Okay, I guess. I don't know. That's a bit more intricate because I mean you could. How do you know that an action is getting the non-perturbable effect from the gauge sector or from, for example, very high scale effects, this ultralight boson? It's a bit tough to say. In one case, you would.
I was thinking perhaps, I mean, if you flow, for example, the mass turns on thermally, right?
Exactly. So that was that's exactly what I was going to say. Usually, when you have a low energy instanton contribution, the mass depends on temperature, right? So you could hope that you can see this kind of fit, but this is happening at Z already a bit far from CMB, so I'm not sure that this can be really investigated.
As a comment on the neutrino fix. So apparently, it's a paper by the Johns Hopkins group where they vary the neutrino mass. They solve the S8, but they make worse the H0.
Okay.
But then, precisely because you are adding a solution to the H0, you can put all together without the, I guess, I don't know. I don't know, you need it, maybe. Yeah, Poulan, Kimberly,
okay,
Bobby.
but it worsens the H0 tension.
Then. It worsens the H0 tension in the vanilla case. So I don't know if then by adding the extra.
Right. So in the case of the action, it does not worsen. Actually, it makes the situation a bit better.
Yeah, but does it worsen within the standard model, and then you add the
early dark
extra
energy,
piece,
yeah.
And I don't know, I didn't read the paper.
Right. Thanks. Yeah.
Any more questions?
Well, I have one. In this new early dark energy model, you're assuming that when this phase transition happens, the energy is released from the, say, the order parameter into the bath.
Yes.
Instantaneously. But this is happening at a very low temperature. So have you written down a coupling and have you checked that? Because, for example, this could be released into lighter stuff and you have like neutrinos or photons, no?
Right.
So either this is very small and you have like a little bit of matter domination that could alter your fit.
Right.
Or if you go to neutrinos have already gone out of equilibrium. So you would alter, you would alter either the CMB or the neutrino thing.
So here I'm assuming that this is a completely dark sector, so it cannot photons, nothing.
So it stays in the dark sector. Like
it has to stay in the dark sector completely. If you reheat 15% of the energy density at CMB into neutrinos, yeah, I mean more. So yeah, I'm assuming here it's completely disconnected from the standard model thermal bath, but you can see. I mean, it will still go into some dark sector thermal bath. Yeah.
So, but related to that, so in that model, it was W of 2/3, right? So
I fixed, yeah, this is what I presented here is an effective model where I'm not exactly addressing the origin, not
But
exactly
that's
checking.
difficult. I mean, I think you mentioned it. W of greater than a third is very difficult.
It's
to
very
get.
difficult. So what I, yeah.
So why not 1/3? That doesn't really.
Yeah, 1/3 does not work enough. So it works better than just dark radiation. So having a transition from dark energy to dark radiation is already better than having only dark radiation at all times. But it doesn't work enough in pushing the value of H0 high enough. So
even with adding an axion.
Even with adding an axion, yeah. So it really seems that you need something that, but again, it doesn't have to be that you. So the hope is that, at least my hope in a sense, it's that you can find a behavior that has a transient state. So it doesn't have to be stiff at all times. It has to be stiff just for a short time after equality, very short time after equality, such that you get rid of this thing essentially, and then you can go to matter, for example. Then it can start behaving like non-relativistic matter once it's completely relevant for compared to the energy density of the background. So in particular, I mean, I've been trying to think about the behavior of gauge theories close to the critical temperature, and whether you can obtain an equational state that is different than 1/3. So that's a, but these are tentative ideas, of course. I don't have. The other thing, you can try to go beyond these models and try to have something that is kinetic energy dominated, like a field with a very steep potential. In that case, you would have an equational state larger than 1/3, but that's a different scenario. Yeah, yeah.
Okay, so if there are no more questions, let's thank Fabrizio again.